Hello everyone, my name is Bao Haishan, and my supervisor is Professor Liu Longxuan. We are from Shanghai Jiao Tong University, which is located in China, Shanghai. Today my topic is about the graphene-enhanced hollow microlattice material and their mechanical properties. I divided my topic into these four parts. Humans are always creative. We not only want a structure stronger, but also lighter. It seems to be a paradox, but nature always be our best tutor. Nature has constructed material with pawns, just like bones, sponges, and honeycombs. But there are still one disadvantage. Because they are randomly porous, they can't utilize the full potential of the structure. So, researchers has fabricated lattice material with a periodic unit cell stacked. The figure 2C shows the unit cell, and the figure 2D is a lattice material stacked by plenty of this kind of unit cell. There are still a lot of room to improve their mechanical properties. Julia Greer has used one way called size effect. That means the smaller of the wall thickness of the unit cell, the stronger of the nano-lattice material. The second way is fabricated lattice material with excellent matrix material, just like ceramic, gold. The last way is structure optimization, just like topology optimization. Our novel idea is inspired by composite material. Fibers in the composite can transfer the load. And what if we put the graphene into nickel phosphorus alloy? That's another form of composite. So we not only fabricated hollow microlattice material, and we want to use graphene to improve their mechanical properties. This figure shows the manufacturing process. First, we use CAD software to design the template, and we utilize 3-dimensional printing to fabricate it. At the same time, we prepare composite base, just like a nickel phosphorus base, and nickel phosphorus graphene electrolysis base. After we activated this template, we put this into the composite plating at 19 centigrade for 25 minutes. Then we get a coated template. After send this to opposite coating to expose inner polymer, and we put this into alkaline aqueous with ultrasonic stirring to dissolve the inner polymer. Then we get the hollow microlattice. The figure 9 shows 4 kinds of different nickel phosphorus graphene electrolysis base. They are 0, 20, 40, and 30 microgram graphene per liter in the solution. To investigate the mechanical properties of the coating and the full-size structure, we built a nano indentation sample to nano indentation and full-size hollow microlattice material to get the in situ compression strengths and the modules of it. For the surface morphology, from this 4 picture, they are fabricated in 0, 20, 40, and 60 microgram per liter graphene base. From this 4 picture, we can see with the graphene concentration increase, the roughness increase at the same time. So the graphene in the coating can increase the roughness of the composite coating, but the coating is still dense without pinholes. to investigate whether the graphene is embedded in the nickel phosphorus alloy or not, we first use concentrated sulfuric acid to etch the surface coating to expose the inner graphene. Just we can see from the picture figure 11a, there is a transparent plant in the coating. To investigate whether it's graphene or not, we use EDS analyze. And there is here is the 0.1 EDS analyze, and here is 0.2. To compare this, we can see that the transparent plant made of carbon mainly. And from this morphology, we can indicate that the graphene is co-deposited into the coating with the nickel phosphorus alloy successfully. To investigate the thickness of the coating, we do the SEM analysis. From the figure 12, we can get the thickness of the coating is about 4.57 micrometers, and we use a sulfur carbon analyzer to get the content of the graphene in nickel phosphorus graphene plating is about 0.31%. To investigate the thickness is uniform or not, we utilize the X-ray microscopy, and this is a picture of the hollow microlattice. The B is one section of this hollow microlattice. Here is a video, shows the thickness, the uniformity of the coating. We can see from this, the thickness of the coating is uniform. That means our stirring process is good enough to make this hollow microlattice material thickness uniform. For mechanical properties, first here is a picture of the Young's model of the different coating by nano indentation. They are different color represent different coating. And figure 15 is the Young's model versus depth curves. From under 40 microgram graphene per liter in the coating in the electrolyte space. And around we can see for the number 2 curve around 30 nanometer, the module is increased sharply. That means the indenter is pressed into a graphene or around the graphene. Our conclusion is graphene in coating can improve the Young's module of the matrix from these curves. And the Young's module of the graphene of nickel phosphorus graphene is 9.4 higher than nickel phosphorus. And optimum graphene concentration in base is 40 microgram per liter. The nano-hardness of the different coating is presented in this figure. Here is a detailed data. From this picture, we can get that the graphene in coating can improve the nano-hardness of the matrix. Optimal graphene concentration in base is 40 microgram per liter. Nano-hardness of the nickel phosphorus graphene under 40 microgram graphene per liter in electrolyte base is 49% higher than nickel phosphorus. Above here is the mechanical property of the base material. Then we investigate the mechanical property of the whole full size of hollow microlattice. Figure 18 shows the mechanical properties of hollow microlattice material. The A is a stress strain curve. The different color represent different hollow microlattice, and the red one is 40 microgram per liter graphene in base in electrolysis. And the B, figure B, is a specific module and a specific strength trend about the hollow microlattice. From this figure, we can see that the graphene matrix can improve the mechanical property of the nickel phosphorus graphene hollow microlattice material, and the optimum specific module of nickel phosphorus graphene is 53% higher than nickel phosphorus. That means this one, and this one. The optimal specific strength, the blue line, blue dots of the optimal specific of the nickel phosphorus graphene hollow microlattice material is 61.4% higher than nickel phosphorus. That means this one compared to this one. The one key point is that optimal graphene concentration in base is 40 microgram per liter. We attribute the improvement in module is from the graphene. Can explain by this equation. And the EC is a module of the composite alloy. Vg is the volume of the volume friction of the graphene. Eg is the modules of the graphene. This equation just like the rule of a mixture in composites. And for the strength, sigma c is sigma c also can attribute to rule of a mixture, and sigma c is sigma m is the yield strength of the matrix plus the yield strength due to load transfer plus the increment in yield strength by hole patch strengthening, and plus the yield strength due to mismatch in coefficient of the thermal expansion between matrix and graphene nanoplanes. And sigma oven is the increment. Delta sigma oven is the increment in strength according to oven strength mechanism. For the nickel phosphor alloy, for the nickel phosphor hollow microlattice material prepared under 60 microgram per liter of graphene in plating solution, the mechanical property decrease due to a large amount of graphene that allow merge in the coating and formed a large size defect. Let's do a conclusion. We developed a novel method that combines nano composite electrolysis plating and 3-dimension plating. The method was used to successfully fabricate graphene-enhanced nickel phosphorus hollow microlattice material. In terms of morphology, the wall thickness is uniform, and the roughness is increased due to introduction of G. In terms of mechanical properties, the specific module and strength is increased due to graphene introduced, and their value, the mechanical properties, reached maximum value when the graphene in base was 40 microgram per liter. The strengthening effect arranged from the combination of rule of mixture and crack arrest performance of graphene. Thanks for listening.